Welcome to acid strength. So we've already talked about how to identify acids and bases, how they react in water. And now we're going to talk about the strengths of acids, because not all acids are as strong as other ones. So for some generic acid in water, we're going to call it HA. The A part is just some generic acid. So we know that we have some proton. If it's an acid, it has to be able to donate that proton. Note that now we're working with the Bronsted-Lowry definition. When we put that in water, we get the conjugate base of our acid, A minus, and we get the hydronium ion, or H plus. So here, the HA is the acid. The water molecule here is our base because that is accepting the proton. The hydronium ion is the conjugate acid of the water, and our A minus is the conjugate base of our HA acid. So, because this is an equilibrium, we can write an equilibrium expression for our reaction. We can write Ka, the A there, or Ka stands for the acid dissociation constant. So Ka is equal to H3O plus, or H plus, times concentration of A minus divided by the concentration of HA. Again, here, these brackets, the square brackets, mean the concentration of whatever chemical species we have inside. So we can write that either as concentration of H3O plus times concentration of A minus over concentration of HA, or we can write it this way, where the concentration of a proton, H plus, times concentration of A minus over concentration of HA. So, strong acids are acids that completely dissociate in water. This means that they are strong electrolytes. If we put something like hydrochloric acid into water, basically all of our hydrogen chloride molecules will dissociate into protons and chloride ions. And they can then move around independently of one another. If only some of them were to dissociate, then it's not a strong electrolyte, it's only a weak electrolyte, and then we don't call it a strong acid, we call it a weak acid. So in this case, with a strong acid, the proton is completely transferred to water, it's completely dissociated, and this means that there are no undissociated acid molecules remaining in solution, and this means that then their conjugate bases have negligible tendencies to become protonated. Because if the conjugate base is a strong base, then that conjugate base will just steal the proton back again. But if all of our molecules are undissociated, if none of our molecules are undissociated, if all of our molecules are dissociated, then that means that all of the molecules that are in the base form are not reacting with the protons that are around in solution. And that means that that base is not a strong base. It's not even a weak base. It's essentially negligible. It doesn't react. It's a weaker base than water is. So we have 6 common strong acids, and you should know these. So you should basically memorize this list. We have hydrochloric acid, HCl, sulfuric acid, H2SO4. Note that this is for the first deprotonation only taking off one of those 2 protons. That second proton is still acidic, but it's significantly less so. It's a weak acid. Nitric acid, which is HNO3, hydroiodic acid, HI, hydrobromic acid, HBr, and perchloric acid, HClO4. So again, note here that we have 1, 2, 3 out of our 6 acids, so half of them are half of our strong acids are halide acids. We've got hydrogen chloride, hydrogen iodide, and hydrogen bromide. Note that hydrogen fluoride, HF, is not a strong acid because of hydrogen bonding. Because the fluoride can form hydrogen bonds, that makes that molecule stronger, and that means that HF is a weak acid. Now, HF is a very, very nasty reactive acid. I would much rather spill some hydrochloric acid on myself than hydrofluoric acid on myself. So the strength of the acid does not necessarily mean that it's going to react more strongly. So the reactivity and the strength of the acid are not the same things. The strength or weakness of the acid is only talking about how much the acid dissociates, how much that proton is removed from the anion. So any acid that we don't have listed here, at least in a general chemistry class, you can consider a weak acid. There are a few other strong acids, but they're basically not common. You're not going to run into them in a general chemistry course. So, on the other hand, weak acids, as compared to our strong acids, weak acids are incompletely dissociate in water. Our strong acids completely dissociated in water, but our weak acids incomplete, which means that only some of our acid molecules are dissociating and transferring a proton to the water to form the hydronium ion. So the lower our probability of dissociation, that means our acid is weaker. So the more our acid is dissociated, the stronger the acid is. The less the acid is dissociating, the weaker the acid is. So weak acids in aqueous solution exist as a mixture of their protonated form and their deprotonated form. So as a mixture of the undissociated form and the dissociated form. Another way to look at this is if we have some HA around, if it's a weak acid, then we have some HA, and we also have some H plus or H3O plus, and some A minus. With a strong acid, we basically have none of this form around, and everything exists over here in these two. But with a weak acid, we have some in this form and some in that form. Or for most weak acids, really most of it exists in this form, unless they're really diluted. But if you have, say, a 1 molar solution of a weak acid, most of it is going to exist in that form, and just a little bit of it is going to exist in this form. Substances with negligible acidity do not transfer a proton to water. So if we have something like methane, if we dissolve methane in water, none of the protons here in methane go to the water. None of the water molecules are donating a proton to the methane. So the methane is not an acid, it's not a base. It's what we say that it has negligible acidity. So now let's look at strong bases. So strong bases, just like the strong acids, dissociate completely in water, and we have more common strong bases. They aren't limited to these guys. The hydroxides of alkali and alkaline earth metals, like lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. You should know those guys. They also include oxides, hydrides, and nitrides. These are the guys that in a general chemistry course, you should recognize these as being strong acids. Again, these first 5 are all the alkali metal hydroxides, and the bottom 3, the calcium, strontium, and barium hydroxide, are the alkaline earth metal hydroxides. So, again, the alkali metal hydroxides and alkaline earth metal hydroxides, the hydroxides of the first 2 columns, excluding hydrogen, obviously, because it's not a metal. Those guys are strong bases. You should be able to recognize those as strong bases. At least for my class, I'm less concerned with whether you can recognize the oxides, hydrides, and nitrides as strong bases. So, on the other hand, weak bases dissociate incompletely in water, just like the weak acids, and the stronger the acid is, the weaker its conjugate base will be. Because if we have our HA dissociating into A minus and H plus, if HA is a strong acid, that means that all of the molecules exist in this form. But if all of the molecules exist in this form, that means that this backwards reaction, where we recombine our conjugate base and the proton to form our acid, if none of them exist in that form, then that means that that reverse reaction is very unlikely. Which means that this A minus, our conjugate base, is a really, really weak base. It's basically not forming the H plus again, or sorry, the HA. And if this is a strong acid, then this backwards reaction essentially doesn't happen at all. And that means that A minus is not accepting a proton, which means it's essentially not a base. We still call it our conjugate base, though. It's just much, much weaker than water is. So note here that the strength of our acid or base has nothing to do with its concentration. You can have a concentrated solution of a strong acid or a dilute solution of a strong acid. You can have a dilute solution of a weak acid or a concentrated solution of a weak acid. So again, the strength of the acid or base has nothing to do with the concentration, and it doesn't necessarily mean that the reactivity is worse or that the acid or base is more reactive. It just means whether or not the acid or base is dissociating in water. So strong acids and strong bases dissociate readily, which generally means that they're highly reactive, although we can have some weak acids that are very reactive as well. That means that they're generally very dangerous to living tissues because pH values outside of a range of about 4 to 8 or so tend to be somewhat dangerous to us. Certainly a pH of 1, like is in your stomach, is dangerous. Any tissue that goes into a stomach, unless it's specifically adapted to live there, will generally die. If you put, say, meat into your stomach, it gets digested. So if your hand goes into somebody else's stomach and it stays there for a few hours, it will eventually get digested away. So this means that strong acids and strong bases need special care when you're handling them because you don't want to get these things on your skin. We've already talked a little bit about one acid that has more than one proton. So an acid can have more than one proton that's acidic. So let's look here at sulfuric acid. So in this case, or if we have an acid that is that can have more than one proton that's acidic, we call that a polyprotic acid. In this case, diprotic means that it's got 2 protons. Triprotic means that it has 3 protons that are acidic. These are the only really common polyprotic acids that we deal with in chemistry, although we can get to things like large proteins that have a great number, over 100 number of acidic hydrogens in them. So whether an acid is polyprotic or monoprotic does not determine the strength of the acid, but the first proton removed from a polyprotic acid is always stronger than the second is always stronger than the third, and so on. So for every proton that you remove, the acid is getting weaker and weaker and weaker. Or alternately, for every proton that you add to a polyprotic base, that base is getting weaker and weaker and weaker. Let's look at the autoionization of water and the reaction between 2 of our water molecules. We have H2O plus H2O. That gives us hydronium and hydroxide. And this means that water can act either as an acid or a base. And again, such a substance is called amphoteric or amfiprotic. So, but now let's look at that same reaction with just a single water molecule. And we have the water molecule dissociating into hydrogen ion, H+, and hydroxide ion, OH-. So, because this reaction is in equilibrium, we can write an equilibrium constant expression. So Kc here is equal to our concentrations of our products, hydrogen ion, times concentration of hydroxide ion, divided by the concentration of our reactants, water. Okay. But remember from the equilibrium section that we can then exclude the concentration of any pure liquid or pure solid. So water is a pure liquid in this case. So that means that that denominator drops out. And now we have Kc is equal to H plus concentration times OH minus concentration. And this is a very special equilibrium. This reaction happens all the time, and we refer to it a lot. And so we're going to give this Kc a very special symbol. And so we're going to assign this Kc value a special name and symbol. We're going to give it the name, the ion product constant, and we're going to write it as Kw. So this is the dissociation of water, the autoionization of water. So Kw then is equal to concentration of H plus times concentration of OH minus. And at 25 degrees C, the value of Kw here is 1.0 times 10 to the minus 14 molar squared here. That's what our units are. You need to remember this 1.0 times 10 to the minus 14. So generally when we're talking about acids and bases, we assume that we're dealing with them at 25 degrees C unless we specify otherwise. And that means that this value, 1.0 times 10 to the minus 14, you should be able to plug in to this side. And that means that now the concentration of our hydrogen ion times concentration of our hydroxide ion is a constant, at least if we keep the temperature constant. So that means that if we have 10 times as much hydrogen ion, we have to have 1/10 as much hydroxide ion. And the water molecules adjust those concentrations automatically. If you put in some acid that is going to raise the hydrogen ion concentration, the water molecules react through this reaction to remove some of the hydroxide ions due to Le Chatelier's principle. So if we have a neutral solution, then we have no other acid or base other than water, and that means that we have equal concentrations of hydrogen ion and hydroxide ion, because the only source of these two is from the autoionization of water. And that means that for every time we produce one proton, we have to be producing one hydroxide. And that means that in a neutral solution, those two concentrations are equal. If we add an acid and we increase the concentration of hydrogen ion, then our hydrogen ion concentration is larger than our hydroxide ion concentration. If our solution is alkaline or basic, that means we've increased the hydroxide ion concentration, and that means the hydrogen ion concentration has to drop. So our hydrogen ion concentration is less than our hydroxide ion concentration. So that was acid strength.